A unique pattern. In chapter 10 on projective geometry, we shall meet the function open parentheses a minus b times open parentheses c minus d divided by open parentheses b minus c times open parentheses d minus a. This is called the cross ratio of the four numbers a, b, c, d. As it is rather a lengthy expression, let us refer to it as a f open parentheses a, b, c, d, which is somewhat shorter. Yes. The order of the letters a, b, c, d is important. For instance, if we wrote f open parentheses a, d, c, d, that would mean open parentheses a minus d times open parentheses c minus b divided by open parentheses d minus c times open parentheses b minus a, which is not by any means the same as f open parentheses a, b, c, d close parentheses. In fact, as you can easily see, it is a reciprocal of the f open parentheses a, b, c, d. If f open parentheses a, b, c, d equal f, then f open parentheses a, d, c, b equal 1 over x, 1 divided by x. Altogether, there are 24 orders in which 4 letters can be written, so that there are 24 different expressions we can form by taking a, b, c, d in different orders. For example, f open parentheses a, c, d, v, f open parentheses d, c, d, a, f open parentheses d, v, a, c. If you have patience to write all 24 expressions out, you will find that there are not all different 6 different values occur, each of them 4 times. You can check the algebraically, or if you like, you can take the particular values, say a equals 0, b equals 1, c equals 2, d equals 3. By taking the numbers 0, 1, 2, 3 in the different orders, you can get the value minus 1/3, minus 3, minus plus 3/4, 4, 3/4, and 4 over 3 for the function. Each value can be got in 4 different ways. For example, 1 minus 1 divided by 3 equal f open parentheses 0, 1, 2, 3 close parentheses equal f open parentheses 1, 0, 3, 2 close parentheses equal f open parentheses 2, 3, 0, 1 equal f open parentheses 3, 2, 1, 0. The 6 values so found are all connected. If we take any one of them and turn it upside down, take the reciprocal, we get another value in the set. If we take any value and subtract it from 1, we get another value in the set. For instance, if we start with minus 1 over 3 and turn it upside down, we get minus 3. Subtracting minus 3 from 1 gives 4. Yes. Turn that upside down and get 1/4. Subtract that from 1 to get 3/4, and turn that upside down to get 4 over 3. Thus, if we are given any one value, we can find the others. Wow! If we start with x and turn it upside down, we get 1 over x. Subtracting from 1 gives 1. Minus 1 divided by x, which may be written open parentheses x minus 1 close parentheses divided by x. This turned upside down gives x divided by open parentheses x minus 1. Subtract from 1 to get 1 divided by open parentheses 1 minus x, and finally turn this upside down to the end with minus 1 minus x. You might think that by turning upside down and subtracting from 1 a few more times, you might be able to get some new expressions. but you cannot. However, many times you've performed these operations, you will still stay within the family circle of x. 1 divided by x, 1 minus x, 1 divided by open parentheses minus 1 minus x, open parentheses x minus 1 divided by x, and x divided by open parentheses x minus 1. If then you were told that f open parentheses a b c d has the value 5, say, you would know that f open parentheses a d c v was 1 over 5, and f open parentheses f c b d was minus 4, because 1 minus 5 equal minus 4, without needing to be told what a b c d were. Wow. For naturally the single equation function of the ABCD, yes, so f open parentheses ABCD equal 5 is far from fixing the four quantities ABCD. The interest of this fact lies in its uniqueness. No other function does what this one does. Wow. Here, of course, we rule out trivial arguments to the function itself. For instance, the function 3f open parentheses a b c d close parentheses minus 2 has the same kind of the property, but we regard this as an old function in disguise rather than as a new function. Again, there are certain comparatively trivial ways of getting a similar property. We might consider a symmetric function, say phi open parentheses abc equal a plus b plus c. The sum of the three numbers does not depend on the order in which they are written. So, if we are told phi open parentheses abc equal 5, we know that phi open parentheses acv equal 5 too, and all the other ways of writing abc would give 5 too, yes. But this is too obvious to be interesting. Slightly less obvious are functions such as a large f open parentheses abc equal open parentheses a minus b times open parentheses a minus c times open parentheses b minus c. If we exchange any two letters, this function changes sign. Thus, large f open parentheses abc equal minus large f open parentheses acv equal minus large f open parentheses cva equal minus large f open parentheses bac equal large f times open parentheses bcd equal large f times open parentheses cav. It has only two values, x and minus x. However many letters are involved, we can always construct symmetric functions like phi, which remain unchanged however the letter are shuffled, and function like large f, which only take two values when the letters are shuffled, yes. But if we want to have more than two values in the set, and to be able to predict all the values as soon as we are told one of them, we must work with four letters, such as a, b, c, d above, and our functions must be cross ratio f open parentheses a, b, c, d, or that function thinly disguised. In this sense, the number 4 and cross ratio f open parentheses a, b, c, d are signed out from all other numbers and functions. An interesting thing is that the uniqueness of function f times open parentheses a, b, c, d can be proved without making any calculations whatsoever. That is to say, by a conventional type of the argument. The proof is quite short and depends on the theory of groups. A unique function is nearly always worth studying if certain towns can only be reached by passing a particular bridge. Traffic on that bridge is likely to be heavy. In the same way, if certain properties are possessed only by one particular function, any problem which involves those properties must be solved by means of the function. Wow! The cross ratio f times open parenthesis ABCD does in fact occur in many branches of the mathematics. You may find it interesting if you have not already done so to verify by elementary algebra the properties stated earlier in this chapter that if f times open parenthesis ABCD equal x, then the 24 cross ratio formed with ABCD or the function of the x stated earlier. This involves a fair amount of work. Later in chapter 10, when we have learned the geometrical significance of the cross ratio, we shall be able to prove these results with very much less labor. Wow! You will appreciate the help that geometry gives to algebra very much more if you have worked at any rate a number of these verifications out for yourself by more elementary method. Incidentally, for anyone learning algebra, it is often more instructive to work one problem by 3 or 4 different methods than to work out 3 or 4 different problems. Working the same problem by different methods, one has a chance of learning how these methods compare with each other in shortness and efficiency. Thus, an experienced outlook is built up. Whoa!